How to build an 800-meter Dubai Tower in the desert. To build the Dubai Tower, the first thing you need to construct is the foundation. If you directly use this kind of foundation, because the contact area between the foundation and the ground is too small, the stress will exceed the soil's bearing capacity, causing a punching effect and making the entire building collapse. If you switch to this type of footing foundation, it can distribute the force well. But the huge pressure will still deform the foundation. Of course, you can increase the thickness of the foundation to solve the deformation problem, but this design can only support small and medium-sized buildings. To support a large building, further improvement is needed. You can treat the entire foundation as one whole piece and build a large reinforced concrete slab. This evenly distributes the load and greatly increases stability. This design is called a raft foundation. Dubai Tower officially uses this design. Its raft is 3.7 meters thick, with a total concrete volume of 12,500 cubic meters, designed in the shape of a desert flower. However, Dubai is located in the desert. Engineers dug down 140 meters and still could not find solid bedrock. If the foundation were built directly on such ground, it would experience severe settlement, causing the entire building to collapse. How do we solve this problem? Let's look at an experiment. Take a thin, sharp spick and insert it into sand. As it goes lower and lower, after reaching a certain depth, the pressure pushing upward becomes larger and larger due to the pressure on the stick, and the stick can no longer go down. Based on this principle, engineers added 194 concrete piles under the raft. Each pile is as tall as a 10-storied building. After that, the combined raft pile structure is placed into the ground. You can see that the raft will also settle, but the settlement depth remains completely within a safe range. At this point, the foundation design is complete. Now we begin construction. First, the concrete piles must be built. A spiral drilling machine is used to drill holes and remove the soil. The problem is that because the soil is loose, the whole walls will collapse during drilling. How to prevent collapse? The solution to collapse is very simple. While drilling, continuously inject drilling fluid into the hole. The drilling fluid applies pressure to the surrounding soil, preventing collapse. After drilling is completed, a hollow steel casing is inserted into the hole. Then, the prefabricated rebar cage is placed inside the casing. Next comes pouring concrete into the rebar cage. After all the concrete piles are completed, construction of the raft begins. Large quantities of high-strength steel bars are assembled and welded. Then pouring begins. Because Dubai's daytime temperatures reach 40 degrees Celsius, construction is usually done at night. During pouring, concrete is mixed with ice to control temperature. The entire raft is divided into 4 sections, and each section is poured one by one until the raft is finished. Windstorms and groundwater problems. But in the desert, sandstorms often occur, causing the entire structure to shake and making the foundation unstable. The solution is to add dozens more reinforcement piles. Another problem arises. The site is close to the ocean. Groundwater will seep under the foundation. Over time, the steel inside the piles will corrode. To solve this, engineers used cathodic protection. The foundation's steel reinforcement is made the cathode, and a mesh is used as the anode. When DC current is applied between them, electrons accumulate on the cathode, preventing corrosion. At this point, the entire foundation is completely built. Constructing the upper structure. Engineers used a hexagonal core tube design, but such a tall and slender structure can topple easily when exposed to external forces. Engineers took inspiration from buttresses on dams. Similar buttress cores were built around the main core. To make them more useful, the buttresses were designed in stepped form, effectively using the space as corridors. Through these corridors, residents can view beautiful high-altitude scenery. These blue buttresses are supported by the green partition walls. The walls are not just room dividers. If we remove them, strong sandstorms would cause the entire structure to bend. Reinforced concrete can bear some tensile stress, but if the stress keeps increasing, even reinforced concrete can fail. So, engineers borrowed the I-beam concept from structural engineering and designed the partition walls in this similar form, allowing the building to withstand large tensile forces. To further increase stability, many structural strengthening layers were added, connected to the load-bearing columns, improving resistance to torsion and bending. A wind-driven resonance problem. But there's a problem. If the buttresses were designed symmetrically, strong winds flowing around the building would create a dangerous fluid dynamic phenomenon called vortex shedding. These vortices oscillate and exert force on the building. If the building's natural vibration frequency matches the frequency of these vortices, strong resonance will occur. If resonance cannot be eliminated, the building could collapse. How do we solve this problem? Engineers used an asymmetrical spiral design. The spiral shape disrupts wind forces and prevents strong resonance. With all these techniques combined, it becomes possible to build an 800-meter Dubai Tower in the desert.